is Lucy Yang on Involutions in the Brauer group in derived algebraic geometry.
Thank you for having me. Can I take this off? Can you all read this? It gets in the way. All right. Thank you for reminding me. I'm happy to be here. Okay, so, and thank you all for coming. I know there wasn't a title, or I sort of failed to submit a title or abstract before the deadline, and I was just thinking just now that if I were some sort of filmmaker or something like this, and I just said, okay, I made a movie, I don't have a title for it, and a bunch of people showed up at the theater anyhow, I'd feel extremely lucky or something like this. Okay, so, okay, great. So, before I get into involutions, the Brauer group, and derived algebraic geometry, I want to talk a little bit about just the story without involutions, so the Brauer group and sort of using derived methods to kind of enhance this. Okay, and then I want to talk a little bit about how involutions fit into this whole story. Okay, so let's get started. Okay, so sort of in the context here. Okay, so okay. I am noticing now that this, okay. Okay, so for the rest of this talk, X is going to be some 2CQS classical scheme. Okay, and I want to remember, what is the Brauer group of X? Okay, the Brauer group, or the classical Brauer group, says, okay, well, let's consider all sheaves of Assoc algebras, or Assoc OX algebras, which I'll denote by curly A. Okay, this has so a sort of prototypical example of an Assoc algebra is the endomorphism algebra of some finite rank vector bundle. Okay, so let me set those equivalent to endomorphisms of the trivial vector bundle, or OX. Okay, I want to consider this collection with the operation, which is tensor, over the structure sheaf. Okay, this turns out to be a group, and this is the Brauer group, as we know and love it. Okay, now to any Brauer class, we can associate to it a cohomology class in H2 of X.
What would it be here?
Sorry? Vector bundle.
So these are all vector bundles or particular ones?
Over any vector bundles. Yeah. Okay, where were we? Right, so to any Assoc algebra, I can associate to it a cohomology class in which lives here. Okay, and sometimes this group is called Brauer prime. Okay, and in particular, this is injective, and this lands in the torsion subgroup. Okay, and okay, so maybe in fact, which is due to, in various cases, due to de Jong and Gaber, is that when X is affine or quasi-projective, this map is an iso. Okay. All right, so we might ask, okay, well, how far does this generalize This is ISO for any x. Okay, and the answer is no. Not in general. I won't sort of get into what these examples are, but if you ask me later, I'll refer you to some. Okay. On the other hand, I want to note this following observation. Okay. So if A is Azamaya over X, okay, then I want to consider the derived category, or the perfect derived category of A. Sorry. A. Okay, so this is sort of A modules, or I guess since this is an associative algebra, you could choose, left A modules in OX modules. Okay, and consider those with perfect homology. Okay, so this is an OX linear stable infinity category. Okay, so this is, okay, and this is stable category. Since I'm only considering the perfect ones, okay, this is in fact going to be a small. Okay, and right, small idempotent complete. Okay, so let me just denote the collection of all such stable infinity categories by modules over dperf of X in small stable infinity categories and exact functors in between them. Okay, I never remember if the infinity is subscript or superscript. Something to this effect. I forgot the idempotent complete here. Okay, and this is modules with respect to the Larry tensor product. Okay. All right. Next, this is just an observation about this category here. Let me give this an abbreviated name. Let me write cat X infinity idem or idempotent complete. Okay. Okay, next, this category of small idempotent complete stable OX linear infinity categories has a tensor product. It's a symmetric monoidal tensor product. Okay. Yeah. Oh, you know what? Okay, I was a little imprecise here. It's not quite the Lurie tensor product. I guess I want to pass to int, take the tensor product, and then take compact objects. Okay. All right. Okay. In here, exactly what I want to do is I want to take two objects in here, take int, take their tensor product over Q co of x, derived Q co of x, and then take their compact objects. Okay. Any questions about this? Are we okay with this? Okay. Great. And then the final observation I want to make is that the condition that A is Azumaya actually implies that dperf of A is invertible. This tensor invertible in cat X infinity idempotent complete. Okay. All right. So definition. This is okay. I'm going to attribute this to sort of separately Toan and but also used by Involutions. Okay, is that if if R is a commutative ring, let me say discrete for the moment. Okay, then the derived Brauer space of R. Oh, I forgot something. Here. In the group of R is what? So let me take invertible, or the group wide of invertible objects in R linear stable infinity, idempotent stable infinity categories. I'm just going to write R here instead of spec of R. Okay. I'm going to call this the derived Brauer space of R. Okay, and this is a connective spectrum. Okay, and I'm going to call pi 0 of it, what should I call it? R of R. This is pi 0 of the derived Brauer space. Okay, so, okay, I say space, but really it's an E infinity, group like E infinity space, yeah? Okay, and this is an abelian group. Okay, oh, right.
What's the symbol?
Where?
The symbol for derived Brauer space.
This?
Yeah.
This is, I've tried to use cursive, but I haven't used it since about 3rd grade. So I tried to write BR in cursive. Is that better? Okay. Great. Ah, okay. And I've just written those two attributions here since there were sort of different sort of groups of people have considered different versions of this story for, right, you could consider a connected the infinity ring instead. Okay, this definition still makes sense. Okay. So there, somehow, I'm just telling one version of the story, but there exists much more general versions. Okay. All right. All right. Theorem. I somehow haven't included an attribution here. All right. In my notes, okay, I'm gonna attribute this to Tolan and Antiogepner, but someone please tell me if I'm wrong here. Okay. Okay, so if I fix R as before. Okay, so the assignment. Okay, a functor really, which sends commutative algebras. Okay, I guess somehow I've committed to R being discrete, but you could take connected to infinity R algebras as well. Okay, it sends, say, S to the derived Brauer space of S, in which lands in connected spectra. Okay, this is an atoll hypersheaf. Okay, question?
Sorry, the above, word above.
Mm-hmm.
In mod blank blank, what can lower blank be and what can what's like other blank supposed to be? Like mod
are there blanks?
like yeah, like mod d perf x and other like yeah,
I'm just trying to parse notation, like mod.
That's one of the things with the subscript.
Yeah. What's the
subscript
subscript you
thing?
want? What goes in the subscript and what goes in the parentheses? Like.
Right, so X is right, the QS scheme I started with.
Yeah.
Okay, so I'm taking, the derived category of X, or sort of the perfect derived category of X. Okay, and I'm considering small, stable, idempotent, complete infinity categories, which with a sort of module structure over this guy,
Okay.
which we regard as an algebra via this dimension, via tensor product.
Cool.
Yeah.
Thanks.
More questions? All right. Okay. So using this this fact about the derived Brauer space. Right. Sorry, I jumped ahead. Okay. Really. Okay. We can. Commutative algebras by infinity instead. Okay, so using this, we can extend this to sort of more global situation. Okay, so definition, X is before. Okay, then the derived Brauer space. Oh, this is perfect. Okay, great. Then the derived Brauer space of X instead of R is I'm just going to take the limit, okay, great, affines mapping to X, okay, Brauer of R. Okay, and then likewise for the derived Brauer group.
This limit, is it over a tall maps from sec R to X, or?
Yeah. Okay, so okay, where do I want to go? Okay, so let me notice, or as a consequence of the observations above, okay, we immediately have a homomorphism. From Brauer of X to derived Brauer of X, okay, which just sends A to dperf of A. Okay, or this is not really a sentence that we have. Consequence of observations 1 through 3. Okay, but even though a priori we may have introduced many more objects by passing to this larger, this different setting, it turns out this is not too far from some objects that we are already pretty familiar with. Okay, so here we go. All right, so theorem. Okay, this is, I think in the generality that I'm stating it, this is due to tau n, but I think Max Lieblich did a lot of work on this as well. On this perspective, okay, which is that X is QC of QS. Okay, great. All right, so there are isomorphisms. Okay, so let me more isomorphisms. Okay, so the derived Brauer group are is isomorphic to h1 of x with the z coefficients cross h2 etal of x with GM coefficients. Okay, I'm going to return to this factor in a second. Is that reaching the limit of what we go? Okay, but now on the other hand, right, this is a spectrum, so I can take pi1 of the derived Brauer space of x. Okay, and this is isomorphic to, right. Oh no, sorry, let me take the loop space based at the trivial Brauer class. This is equivalent to pick of the derived category, or the perfect derived category of x. Okay, and now if I take pi0 of this guy, okay, then this is, I guess if I take pi0 of this guy, then that's isomorphic by a result of Faust to classical pick of x, so honest to goodness line bundles without any sort of shift. Okay, that's h0 etal of x with z coefficients. Okay, so what is this isomorphism? It says up to a shift, which is what this is remembering, any invertible object here comes from an invertible object, or it's an invertible discrete or classical object over x. Okay, so what I want to do is, and what is this? This is h1 etal g with GM coefficients. Okay, and this is some sort of artifact of working with the derived in the derived setting. Okay, so what I want to do is now, if I return to this first line here, right? Okay, so if I could ignore the factor on the left-hand side, then okay, great. Then this is the group that I wanted to access via Assoc algebras that I couldn't quite. Okay, without some assumptions. Okay, but where is this factor coming from? Just think about it as an artifact of working in the derived setting, like this guy.
And
Okay.
this computation is true for which kind of x?
Sorry?
This computation. For
QCQS.
So, sorry?
QCQS.
Okay.
Yeah.
Even for the right one. For the right one as well.
Yeah. You mean derived schemes?
Yeah.
Yeah.
But one more. What is the map? Sorry.
Wait, which one?
The top one. The first one.
Okay. Let me think about this for a second. Okay, actually, can we chat about this after? Sorry, I don't want to go on too much with digression. But yeah, that's a great question. Okay. Okay, so if we ignore this sort of, or if we sort of, maybe if we accept this additional factor, then we see that the sort of passing to this, this derived Brauer space, okay, allows us, gets us the cohomology theory that we want. Okay, I've forgotten something. Let me, okay. So let me, okay. A generalized Assoc. Okay, generalized or derived. I somehow the terminology hasn't settled or something. Your generalized Assoc algebra over x. Okay. Is an E1 OX algebra in D perf x. Okay, so that the canonical map. Can you still see this? Got one more one.
Oh, there.
A little bit more. Oh, that might just be lost forever. Okay, the canonical map write a tensor over x. This is a derived tensor. I'm going to write the derived tensor product once, and then everything is going to be derived. No, is that confusing? It's derived. Great. A tensor A up is equivalent to derived endomorphisms of A over X. Okay. This is supposed to be X. Okay. All right. All right. Now, theorem. Again, site to win and anti-vector. Is that suppose given an object or a point in the derived Brauer space of X, okay, then C is equivalent to the perfect derived category of some generalized Asamaya X algebra. And the idea here is that if, okay, so maybe the way that I've stated it is a little bit funny because I'm not working in PRL, okay. But yeah, the idea here is that we want to, in say, Towen or Inter-Gepner's work, we're really considering not necessarily C, but end of C, okay, and we want to find a compact generator for end of C. So find a compact generator for end of C. Okay, then end of C is equivalent to modules. Okay, if my generator is G, then it's equivalent to modules over the endomorphism ring. Of my generator. Okay. And the idea is that if you have generators Zariski locally, right, then you can produce a generator globally. All right. Okay, so now if we put together this theorem with the last result that I've stated over on the upper right-hand board, then we see that if we allow ourselves to consider not just classical Asamaya algebras, but also the derived or generalized ones, okay, then every class in H2A tall GM can sort of be regarded as some class associated to some generalized Asamaya algebra. Okay. All right. So hereafter. I want to talk about what happens with involutions. Thereafter, let me fix X a scheme with an involution. So in other words, some automorphism of order 2. Okay, and I want to fix a good quotient. Okay, what does that mean? Do we want to see the definition of good quotient, or do we just want to know what a couple of examples are?
I want to see the definition.
Huh? You want to see? All right. All right. So this means that pi is invariant. In other words, if I take pi of sigma, this is equal to pi. Okay. Pi is affine. Okay, and if I consider the map from OY to the push forward of the structure sheaf on X, okay, so here I have a sigma action. I'm just going to call it sigma instead of adding more decorations. This induces an isomorphism from OY to the strict fixed points of this action. Okay, so this is what it means for pi to be a good quotient. Okay, and maybe a remark is that this good quotient always exists if in fact it exists if and only if every C2 orbit in X is contained in an affine open subscheme. Okay, so any sort of example that you might want to consider for geometric reasons will probably be nice like this. We're just excluding pathological examples like taking the line with the doubled origin and then swapping the doubled origin points, for instance. Okay. Okay, so there are two special cases, or there are a couple of special cases. Let me tell you what they are. Special. Okay, so we can always take the involution to be the identity. Okay, in which case you can check, not too hard to check, that pi is equal to the identity works as a quotient map. Okay, and in particular, that means that y is equal to x. Okay. Those of you who do genuine equivariant homotopy theory, or just equivariant homotopy theory, I don't know, might squint at this and say, aha, okay, we have a trivial action, what about the free action? All right, so now I'm going to present this in a slightly different way. Okay, if x to y is quadratic état, okay, then I have a Galois action here. Okay. All right, and in general, a good quotient is going to look like a sort of mix of these two special cases. Right, we have a free action, we have a trivial action. Let me just sketch out what, right, so if R is a commutative ring, there's a C2 action. Okay, then I can consider spec of R that same action. Okay, and that maps to spec of the strict, not the homotopy fixed points, but the honest to goodness fixed points. Okay, and this is an example of a good quotient map. Okay. Okay. So, all right. If A is Asmaya over X, okay, then an anti-involution on A, again, I'm going to say of the second kind, although this is not, some folks use different terminology for this. Okay, is an iso of associative algebras from A to the pullback along sigma of the opposite algebra. Okay, so that if I restrict lambda to the center, okay, what is the center? The center is the structure sheaf. I'm going to ask for this to be the action of sigma on the structure sheaf. Okay, and furthermore, I'm going to ask for lambda to satisfy, to be of order 2, except that doesn't quite make sense. I have to add some decorations. Okay, and so that this formula will now parse. Okay. Okay, the sort of standard example of this is that if V is a vector bundle on X, and L is a line bundle, classical line bundle on Y. Okay, and I have a non-degenerate form on V. Okay, what do I mean by that? And given F from V tensor twist of V to the pullback of my line bundle. Okay, so F is non-degenerate, or in other words, if I take the adjoint, this is an isomorphism. Now I have to interrupt the sentence here to erase. Okay. All right, then, okay, so F is, the adjoint of F is an isomorphism, that's a non-degeneracy condition, and I'm also going to ask for F to be Hermitian in some appropriate sense. If I pull back F along sigma, this is, I get F back. Okay, then, endomorphisms of V over OX, okay, has an anti-involution. I'm just gonna stop writing of the second kind. Okay, and what is that? That's given by sending some matrix, if you will, A, to, let me conjugate with an adjoint of F and apply sigma. Oh no, adjoint. Okay, so I want to refer to this collection as L ranges over all possible line bundles over Y and V over all vector bundles over X, and all such forms F to be the sort of standard examples. Was there a question? Okay. All right, and I'm going to define the involutive Brauer group of this sort of collection of data. Let me just write this. So X with this quotient, okay, to be Brauer X, or I'm going to suppress Y from notation. Okay, and I'm going to write this is all such A and lambda, where A is asamaya over X, and lambda is an anti-involution on A. Okay, I claim that I can tensor two together over OX, and I still get an anti-involution on their tensor product. Okay, and now I'm going to set the standard guys equivalent to OX. which has a canonical Hermitian form. Okay. All right. So let me. You're right. The countdown clock is very. I can't forget that it's there. All right. Okay, I want to notice something. I'll make an observation. Okay, so given all of this data, a scheme and a good quotient, if I just have any map of schemes, then I have a pullback on any kind of cohomology theory. Okay, it turns out that in this case, I also have a transfer. Okay, so I think it's not, it's pretty classical that if, okay, let me, yeah. Okay, so in case, or special case number 1, okay, the existence of an anti-involution implies that if I consider the Brauer class, or the cohomology class associated to my algebra, then it's 2 torsion. Okay? And on the other hand, if I consider special case number 2, then the existence of lambda implies that the co-restriction of the Brauer class of A is 0. Okay, and this is going to live in H2 étal of Y, two coefficients. Okay, but an anti-evolution is, here it just says this in two. Oh wait, no, here? Oh, co-restrictions, right. This is, I'm applying a map. This is a transfer map of cohomology. Yeah, okay. So here, we've noticed that if A has this structure, then the cohomology class associated to it has some property. Okay, but theorem of Parimola-Srinivas is that we can really understand what kinds of structures are here. So okay, is that if phi is quadratic étal and 2 is invertible in the structure sheaf, okay, then maybe I should write y. Doesn't really matter. Okay, then let me. Oh, sorry. Okay, let me say this. Qualify you later. Okay, this then there is an exact sequence. Okay, so if I take the involutive Brauer group of X, okay, I can forget the involution. That lands me in Brauer of X. Okay, I have the cohomological transfer map goes from Brauer of X to Brauer of Y. Okay, and I can continue this exact sequence to the left with pick. This is again classical pick of Y and pick classical of X.
Move the board up, please.
Sorry? Oh, yeah. Okay, and this. Okay, and really, this is true when Brauer is equal to Brauer prime for x. Okay, but I'm not going to worry about that. So up to here. Okay, so we've seen how this sort of categorified perspective is helpful for studying H2 étale with GM coefficients. Okay, but what if we add in the data or the structure of some kind of involution? Okay, so shifting gears a little.
It's about follows the torsion and not the center technology.
Yeah. Okay, so where do I want to? Okay, so a theorem due to the 9 authors. Gomez. Okay, great. So as I'm writing down these names here. Okay, so these 9 authors, okay, have defined a sort of a suitable replacement or sort of enhancement, if you will, of these idempotent, complete, stables, small stable, or linear infinity categories. So I'm just going to assert that this exists, even though along the way, even though in the context of all of the work that they have done, writing it in this way is a little bit odd.
We're gonna have to do a few talks.
Okay, great. Okay. There is a symmetric monoidal, or I guess, okay, this follows from work of theirs, plus a little bit, plus epsilon additional work. Okay, there's a symmetric monoidal, infinity category. And write cat P X. Okay, I'm going to call these OX linear Poincare infinity categories. Okay. With a forgetful functor to let me just suppose I've taken the idempotent complete ones. Times, okay, and this maps down to the category that we considered earlier. Okay, and instead of telling you what that is, great, you can ask Fabian. Roughly. Oh no, you can't see this at all, can't you? Is that okay? Yeah. Okay. Okay. Roughly. Okay. An object of this guy. Okay. Is a pair. C kappa. The kappa is some functor. C lives down here. Okay, and kappa is some additional structure that allows us to talk about Hermitian forms on objects in C. With satisfying certain conditions. Maybe now is not the best time to get into what they are. Okay. So oh, actually, you know what? Perhaps it would be here. Here's an example. C, I take d of x, and kappa is, if I just take a vector bundle on x, let me not worry about what it is, then I can consider Hermitian forms on my vector bundle. Okay, and this is a sort of prototypical example of what of the kind of object I want to consider. Okay, so definition. I'm going to consider the, okay, so if I'm back in case number 3, okay, great. Okay, so okay, I want to define the involutive Brauer, I guess, sorry, derived involutive Brauer group or space of R with all this structure, okay, is invertible, is the groupoid of invertible R linear Poincare infinity categories. Okay, and I'm just going to define, oh no, this is supposed to do, okay, great. EBR R is just pi 0 of the connective spectrum above. Oh, have I lost that forever? Okay. So, what is the relationship of this to the classical involutive Brauer group theorem? Okay, if A is asymptotic with anti-involution over my fixed scheme with involution and group quotient. Okay, and either 2 is invertible in the structure sheet of X, or pi is quadratically tall. Okay, then, okay, then dperf of A has a canonical lift to OX linear Poincare infinity categories okay, and also this lift is invertible. With respect to the symmetric monoidal structure, I asserted existed, but didn't tell you what that was. Okay. All right. And you know what? Maybe I'll just continue with this board here. So we can pick those cases up. All right, and I prepared a joke and went with something else. I was going to say something like, how is this related to the telescope conjecture? I don't know, it seems really far away, but if you use the telescope, you can see it really well. But maybe the moral of the story is that something funny happens at the prime 2. Okay, and so we have some expectations for what happens away from these cases, and I think it's going to be related to a trivialization of A, but it's a little bit more subtle than that, I think. Okay. Oh, or trivialization along some of those subscriptions. Okay. And what else? Okay, so here. Okay. Okay. Then, okay, let me just state this. Case. Case 3. Although we expect this to work much more generally. Okay, so if 2 is invertible, okay, then there exists a symmetric monoidal functor from X, X is just R, okay, R linear, idempotent complete, small stable infinity categories to small stable infinity categories which are linear over the strict fixed points, and also idempotent complete. Okay, I'm going to call this the norm. Let's see one in a second. And a fiber sequence of connected spectra, okay, where we have, on the one hand, the involutive Brauer spectrum, yeah, I should write R, mapping to, oh, sorry, the derived involutive Brauer spectrum mapping to the derived Brauer spectrum of R, mapping to the derived Brauer spectrum of the fixed points. Okay, and this map is induced by this functor above. Okay, and I was going to explain a little bit more about how the derived involutive Brauer space is related to the derived Brauer space, but instead of kind of explaining that, let me just state one example so that we sort of have a notion of what these. Okay, so now let me consider, let me just tell you the sort of the punchline of this story, which is that if K is an algebraically closed field, okay, and I consider it as case 1, okay, so in other words, you know, my involution is identity, okay, then the involutive Brauer group of K here, with identity, involution, oh no, I didn't put a star earlier, sorry. Okay, is Z, when the characteristic of K is 2, and it's Z mod 2 cross mu2, when the characteristic of K is not equal to 2. Okay, and roughly what we might think of as this is kind of saying is it's saying, okay, well, when, oh no. Yeah, okay. So when the characteristic of k is not equal to 2, then we sort of have a distinction between, this kind of comes from the distinction between anti-symmetric forms versus symmetric forms, say on vector bundles or something more general. Okay, but that distinction goes away in characteristic 2. Okay, so we kind of expect these various moduli spaces associated to these things, these objects, to be kind of to behave kind of strangely near 2.
Sorry, when you write derived Brauer's group is what do you mean? I feel it's just a bit of
Oh, sorry. You mean,
okay.
is that better? Yeah.
Okay.
All right. Yeah, sorry for going over, and thanks for having me.
Any questions?
Maybe you would have said this if you had more time, but is there some connection to the total homology?
Right. So, yeah, let me look at what I want to say about that. Okay, so maybe what I want to say is that there is a sense in which the involuted Brauer space is also an atal hypersheaf. Okay, you have to be but you have to be a little bit careful about what you mean by that, yeah, because we can't, like, what am I going to say? It's sort of not local on X, right? Because you have this involution. Okay, so you kind of have to do this locally on the quotient on Y. Okay, so indeed you have a sheaf. Okay, I think it's, if we just look at this, it's like maybe a little bit less clear. What am I going to say? I don't think I can just say, okay, it's the cohomology of some associated to some like constant sheaf. So I think it's going to be a little bit more subtle, unless I say, okay, well, let me just restrict to a scheme where, like a scheme over a field. Okay, so then, or I've like fixed the characteristic, and then I think it's going to behave a little bit better, and I think there you could more directly relate it to atal cohomology. Sorry, I'm not sure if that made sense, but let me know.
Do you have a connection between this fiber sequence and the sequence in schedules?
Yes, that's a great question. So let's see. Okay, so what is this? This is, so if Brauer is equal to Brauer prime for X, okay, then you have like H2 atal with coefficients in GM, and then here you pick up an extra H1 atal with this additional factor. Yeah, so you kind of have to project, some summands away, but I expect to get this once you project away extraneous summand. But it's work in progress, so things may change.
Okay.
Yeah, so from what I understood, how you obtained the derived Brauer group was observing that sort of mod R or D of R is commutative algebra in Kant-Perf, and then you can take modules over that, and that is a tensor product, so you can look at tensor invertible objects. And then abstract nonsense, if you take loops of that, you just get the Picard spectrum. Right, so you could technically sort of iterate that procedure and hope to get sort of further de-loopings of the Picard spectrum. So you could look at like tensor invertibles in like modules over D of R, and that would then sort of give you a de-looping of the Brauer group. Do you expect to like to find interesting informations in this like further de-loopings, or are they just not accessible?
That's a good question. I think much less is understood about that, and certainly I haven't really thought about it that much. But I'm under the impression that the person to ask here, or one person to ask, is Runa. I'm not sure if I'm saying his last name correctly. Runa, and perhaps other folks have thought about this as well, but he has some paper on this. Probably that's a starting point.
Because I thought then you don't just get a connective spectrum, but this might assemble into like a a full spectrum, non-connected spectrum.
Yeah, I think Lynn has some question in that paper about whether or not that's even an atoll sheaf. So I think there's like even sort of more basic questions right before you say, okay, well that's going to be some H3 atoll, you know, H whatever
Yeah,
atoll.
yeah.
Right? You need to sort of establish what's more basic.
Can you say something about the conception of non-concrete? It's too hard.
Maybe I can say something. There's a formula you might guess it to be, which is something like this turns out to roughly work. I can say more later.
The canonical lift of D per K to cat P is which one? Is it the generally symmetric I should think about?
Oh, here.
Yeah.
Right, so actually what I've done here is I've made the geometric fixed points 0. Okay, so all of those distinctions collapse. Yeah, right, because the sort of distinction between genuine symmetric versus quadratic, that sort of was...
Who is the unit? Yes, also in the quadratic guitar case.
Hmm?
So you have two assumptions there. Either 2 is invertible or the other one?
Yes.
Does that follow also the same case?
Yeah, I mean, right, like, okay, roughly what you're looking at with this quadratic atoll case is something like, and then this like swap action.
Thanks.
All right, so we have some refreshments for our welcoming reception waiting for us right outside the door, so let's thank Lucy.